Good day, everyone. I'm Renz Angelo Di Calzada, and my topic for chemistry this week is all about molecule of elements and molecules of compounds, and that is for part one. Molecule is defined as two or more atoms of the same element, or different elements that are bounded together. Let us try to differentiate molecule and compound. So what are the difference between molecule and compound? When we say molecule, those are the smallest units of a compound that retains the characteristics of the compound. And molecule also is the smallest particle of a substance that retains the chemical, a group of like or different atoms held together by chemical forces. And when we say compound, that contains atoms of different elements chemically combined together in a fixed ratio. A compound is also represented using a formula, and the list of compound is endless. So let us begin with the first topic, which is all about the molecules of elements. The molecules of an element are, by definition, all composed of the same atoms. For example, oxygen gas or O2, and they share molecular bonds, which means they are bonded by sharing electrons between them. In this case, two oxygen atoms are bonded into an oxygen molecule by sharing electrons. Another example for molecules of an element are the homonuclear diatomic molecules. A heteronuclear diatomic molecule consists of two of atoms of the same element combined. Actually, there are seven diatomic elements. As you can see on this slide, we have hydrogen gas. We also have nitrogen gas. Another one is oxygen gas. We have also fluorine gas. Another is chlorine gas. We have also iodine gas, and the last one is the bromine gas. These seven elements are so reactive that they can be found very often bonded with another atom of the same type. Other elements exist as molecules. For example, sulfur normally exists as an 8-atom molecule or S8, while phosphorus exists as a 4-atom molecule or P4. Molecular art of S8, as you can see on the screen, the illustration of sulfur and P4 of phosphorus molecules. If each green ball represents a sulfur atom, then the diagram on the left represents an S8 molecule. The molecule on the right shows that one more or one form of elemental phosphorus exists as a 4-atom molecule. Let us proceed on the next topic of this discussion, and it's all about molecules of compounds. Molecules of compounds have atoms of two or more different elements. For example, water or H2O has three atoms and two hydrogen atoms and one oxygen atom. Another is methane, which has a chemical formula of CH4. It is a common greenhouse gas that has five atoms, one of carbon and four of hydrogen atom. Let us proceed on the part two of this discussion, and that is all about the structure and properties of molecular compound. Let us discuss now the representing molecules through a structural formulas. Chemical formulas only tell us how many atoms of each element are present in a molecule, but structural formulas also give information about how the atoms are connected in space. In structural formulas, we actually draw the covalent bonds connecting atoms. And in this section, we are going to look at the chemical formula for ammonia. Now, let's consider its structural formula. Two structural formulas for ammonia. The formula on the left gives only a two-dimensional approximation of molecular structure, whereas the formula on the right shows the orientation of atoms in space using dashes going into the plane of the page and wedges coming out of the plane of the page. The two dots on nitrogen in the right formula indicate a lone pair of electrons. From both of the structural formulas, we can see that the central oxygen atom is connected to each hydrogen atom by a single covalent bond. Keep in mind, however, that atoms and molecules, just like everything else in the universe, exist in three dimensions. They have length and width, and as well as depth. In the structural formula to the left, we are only seeing a two-dimensional approximation of this molecule. However, in the more detailed structural formula on the right, we have a dashed line to indicate that the rightmost hydrogen atom is sitting behind the plane of the screen, while the bold edge indicates that the center hydrogen is sitting out of the plane of the screen. The two dots above, here, the two dots above, the nitrogen indicate a lone pair of electrons that are not involved in any covalent bond. To help show this three-dimensional shape even more accurately, we can rely on space-filling models as well as ball and stick models. Let's consider both of these models for ammonia. So this is an example of a space-filling models as well as ball and stick models. A space-filling model, which can be found on the left side of the picture, and a ball and stick model on the right for ammonia. Nitrogen atoms are depicted in blue and hydrogen atoms are depicted in white. The left-hand image shows the space-filling model for ammonia, and the nitrogen atom is depicted as the larger central blue sphere, and the three hydrogen atoms are depicted as the smaller white spheres of to the side, which form a kind of tripod. The overall shape of the molecule is a pyramid with nitrogen at the vertex and a triangular base formed by the three hydrogen atoms. So, as you will learn when you study molecular shapes later on, as well as molecular geometry, which will be discussed to you by Mr. Ryder Jan Bartolini, this type of arrangement is known as trigonal pyramidal. The main advantage of the space filling model is that it gives us a sense of relative sizes of the different atoms. For example, nitrogen has a larger atomic radius than hydrogen, And the right-hand image shows us the ball and stick model for ammonia. And as you might be able to guess, the balls represent the atoms, and the sticks that connect the balls represent the covalent bonds between the atoms. The advantage of this type of model is that we can get to see the covalent bonds, which is also you which is also allow us to more easily see the geometry of the molecule, as you can see now on your screens. Let us proceed now on the fourth topic of this discussion, and that is all about the properties of molecular compounds. Covalent or molecular compounds contain atoms held together by covalent bonds. These bonds form when the atoms share electrons because they have similar electronegativity values. Covalent compounds are a diverse group of molecules, so there are several exceptions to each rule. When looking at a compound and trying to determine whether it is an ionic compound or covalent compound, it's best to examine several properties of the sample, and these are properties of the covalent bonds. Number one, most covalent compounds have relatively low melting points and boiling points, while in an ionic compound are strongly attracted to each other. Covalent bonds create molecules that can separate from each other when a lower amount of energy is added to them. So therefore, molecular compounds usually have low melting and boiling point. Second property of a molecular compound is or covalent compounds is that it usually have lower enthalpies of fusion and vaporization than ionic compounds. The enthalpy of fusion is the amount of energy needed at constant pressure to melt 1 mole of a solid substance. The enthalpy of vaporization is the amount of energy at constant pressure, where it is required to vaporize 1 mole of a liquid. So on average, it takes only 1% to 10% as much heat to change the phase of a molecular compound as it does for an ionic compound. Third property of covalent compound or molecule of compound is that they tend to be soft and relatively flexible. This is largely because covalent bonds are relatively flexible and easy to break. The covalent bonds in molecular compounds cause these compounds to take form as gases, liquids, and soft solids. As with many properties, there are exceptions, primarily when molecular compounds assume crystalline forms. Fourth property of covalent compounds is that they tend to be more flammable than ionic compounds. Many flammable substances contain hydrogen and carbon atoms which can undergo combustion, a reaction that releases energy when the compound reacts with oxygen to produce carbon dioxide and water. Carbon and hydrogen have comparable electronegativities, so they are found together in many molecular compounds. So later on, you will know more about electronegativities in the next reporters. Number 5. When dissolved in water, covalent compounds don't conduct electricity. Ions are needed to conduct electricity in an aqueous solution. So, molecular compounds dissolve into molecules rather than dissociate into ions. So, they typically do not conduct electricity very well when dissolved in water. Sixth property of a covalent compounds is that many covalent compounds don't dissolve well in water. There are many exceptions to this rule. Just as there are many salts, which is an example of an ionic compounds, that don't dissolve well in water. However, many covalent compounds are polar molecules that do that do dissolve well in polar solvent, such as water. Examples of molecular compounds that dissolve well in water are sugar and ethanol. Examples of molecular compounds that don't dissolve well in water are oil and polymerized plastics. But we have also to note that network solids are compounds containing covalent bonds that violate some of these rules. For example, diamond cons- it consists of carbon atoms held together by covalent bonds in a crystalline structure. Network solids typically are transparent, hard, good insulators, and have high melting points. Let us now proceed on the third part of this report, and that is all about the strength of covalent bond. Strength of covalent bond. The strength of covalent bond depends on the bond length, the distance between the two bonded nuclei at the position of maximum attraction. And as the number of shared electron pairs increases, the bond length decreases. The shorter the bond length, the shorter the bond. So, the weakest bond is a single covalent bond and the strongest is a triple covalent bond. So, if there is only one bond, so therefore we will the length of the bond is longer. If there are two bonds, then therefore it is shorter than the single bond. If there are three bonds or triple bonds, then therefore triple bonds is the shortest among all the bonds. And in terms of its strength, the shorter the bond, the the hardest it is to break. The longer the bond, it is easier for it to be broken. The strength of the bond is based on can be explained through the following. First, we have the bond dissociation energy is the amount of energy needed to break a covalent bond. So breaking bonds always requires the addition of energy. Next, we also have endothermic reactions that occur when a greater amount of energy is required to break the existing bonds than is released when the new bonds form in the product molecules. And we have also the exothermic reactions occur when more energy is released, forming new bonds than is required to break the bonds in the initial reaction. So that would be all my report. Thank you so much for listening. Here are my references. Good day, everyone.